Not every feature earns its place. Permutation Feature Selection shows which columns you can remove without hurting validation performance. This is the pattern you'll be able to implement by the end, which learns feature importances and evaluates the trimmed model. I'm Professor Pine, teaching AI foundations with simple Python. Permutation Feature Selection solves a familiar problem. You train a model and then ask, which inputs really move the needle? Fewer features can make debugging easier, cut cost, and speed inference. The goal is a smaller model that keeps validation performance within an acceptable margin. This is especially useful on tabular data, where many candidate columns are noisy or overlap. At a basic level, permutation importance measures how much performance drops when a column is randomly shuffled. If shuffling a column barely changes accuracy, it probably carries little signal. If accuracy collapses, that column matters. The method is model agnostic and intuitively easy to explain. Just be careful. Very correlated features can hide each other. We'll walk a compact workflow. Train a baseline classifier. Measure permutation importances. Pick reliably useful columns. Refit a reduced model and compare holdout accuracy. The code keeps every decision auditable and easy to follow. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need a reproducible toy dataset so our examples are stable and repeatable. This snippet seeds a reproducible tabular dataset and trains a scikit-learn LogisticRegression to anchor the baseline. The random number generator, RNG, first creates sig as the driving signal and draws two unstructured noise columns that will challenge the classifier later. NumPy column stack builds X by mixing sig with a correlated companion column and the raw noise matrix, while the label Y is synthesized with a linear rule plus Gaussian perturbations. Train test split keeps the class balance intact. Then logistic regression with max iterations set to 500 fits quickly on the reduced dataset, and the classifier score reports the holdout accuracy. The printed baseline accuracy shows how well the full feature set fares before any pruning. The model trains fine, but we still don't know which inputs truly matter. Next, let's measure each feature's effect directly. This example uses scikit-learn permutation importance to quantify how each feature disrupts the already fitted logistic model when shuffled. Feature names align human-readable labels with the NumPy columns, so the ensuing ranking is interpretable. Permutation importance runs 20 random shuffles per column. Returning a perm object whose importance is mean array, we sort to surface the least helpful signal. Increasing the number of repeats would stabilize the estimates at extra cost, whereas reducing it makes the ranking faster but noisier. The printed weakest feature and score drop identify the current top candidate for removal and give a sense of how much the model depends on each column. A ranked list is helpful, but rankings can be noisy. We need a small stability test to keep only the features that show consistent importance. This code casts the permutation statistics into a pandas data frame to judge which features are reliably helpful. Summary collects the feature names plus mean and standard deviation columns from the permutation result and sorts them so the strongest signals rise to the top. The stability mask applies a mean minus 2 standard deviations rule, echoing a conservative confidence interval to weed out shaky attributes and avoid keeping features that only look useful by chance. Using summary lock keeps only the names that survive this variance filter and converts them into the keepers list for reuse. The printed reliable features list shows which columns stay above the noise floor and how many will be retained. With a shortlist in hand, we must check whether the trim set preserves holdout performance. So, we refit on the reduced matrix and compare. This code rebuilds the model on the reduced feature matrix to validate a leaner scikit-learn pipeline. NumPy, where teams with NumPy isn't to translate the textual keepers list into column indices that slice the training and test arrays. LogisticRegression refits on X-train, reduced while preserving the original Y-train labels, ensuring any performance shift stems solely from the feature drop. The scorer then evaluates the slimmer classifier on matching columns from X-test reduced to obtain the new holdout accuracy. The printed reduced accuracy confirms whether the pared down model keeps pace with the baseline and whether simplification comes at an acceptable cost. Finally, we summarize what was removed and quantify the net metric change so stakeholders can decide. This example contrasts the trim setup against the original measurements to close the feature selection loop. NumPy set difference reveals which names disappeared, so you can communicate the simplification explicitly. Subtracting the original accuracy from the reduced accuracy quantifies the net effect of removing noise features without rerunning training. If the delta drifts upward, you gained accuracy, while a mild negative value highlights the acceptable cost of simplification. The printed, removed features and accuracy delta summarize the trade-off for decision makers and provide a clear number to guide follow-up actions. Take this pattern into a real project by swapping in your production split, logging the removed columns, and running a quick timing check on the trimmed model to measure latency changes. The same decisions and thresholds apply. Just scale the data and model. Recap: Permutation Feature Selection tells you which features the model actually relies on by measuring the performance drop when you shuffle a column. Use it when you want interpretable, model-aware pruning of tabular inputs. One caveat: highly correlated features can mask each other, so treat grouped predictors with extra care. Next step: scale this experiment to your full dataset and add timing and accuracy checks so you can trade off inference cost against the small accuracy delta. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.